This is the city of Boston, Massachusetts. Across the Charles River is Cambridge, home of MIT, the Massachusetts Institute of Technology. Less than 5 miles from the center of the metropolitan area, close to the MIT campus, is the site of a new nuclear research facility, the Massachusetts Institute of Technology Research Reactor, the MITR. This facility, which was engineered and constructed by ACF Industries Incorporated, includes the world's first heavy water research reactor to be built for private use. Its proximity to the Institute makes possible full utilization by the MIT staff and the complete integration of the teaching and research programs. This reactor will also be available to groups representing industrial organizations, medical research, and other varied fields. It is a heterogeneous research reactor to be operated initially at 1 megawatt power. The reactor is cooled and moderated by heavy water. This assures maximum stability and safety features. At the same time, it provides the largest possible thermal neutron volume for research and experimentation. The fuel is standard 18-plate MTR-type fuel elements with approximately 105 grams of U-235 in each element. This fuel element was chosen because of its proven reliability and large heat transfer surface. The reactor core consists of 19 fuel elements spaced in an array comprising 2 concentric circles around the central element. This core is centered in a 4-foot diameter aluminum tank filled with heavy water. The aluminum tank is surrounded by a 2-foot layer of graphite contained in a gas-tight Barrel-lined steel shell filled with helium. Just outside of the aluminum tank is a steel and lead thermal shield with embedded pipes for circulating cooling water. The reactor is surrounded on all sides by a dense concrete biological shield adequate to reduce radiation dosage to less than 1/10 allowable tolerance. The site chosen was formerly a parking lot in an industrialized section of Cambridge. Adjacent to the site are 2 buildings which will be used as classrooms and offices. Ground was broken for the project June 6, 1956, and within several months the foundation mat was completed, the access pipes placed, and the first course of the steel containment shell put in place. Construction of the second course of the steel shell began with the installation of the hot plug storage tubes. The steel shell, a 74-foot diameter cylindrical building with an ellipsoidal dome, is of all welded construction. Its purpose is to prevent contaminated water or gases from escaping to the outside atmosphere in the event of a nuclear incident. The plates of this shell are a 3/8-inch steel, and the building is designed to withstand a 2-pound internal overpressure. In addition, the steel shell meets the specification requirements that it will not leak air at a rate exceeding 1% of the building volume per day for each pound of overpressure. The steel containment shell extends 13 feet below grade to the base slab, and the height of the completed building is approximately 50 feet above grade. These 3 10-foot courses were erected in 1 8-hour working day. A biological shield of heavy or dense concrete surrounds the reactor proper. The mixture consists of small steel punchings averaging 1/4 inch in diameter, large steel punchings averaging 3/4 inches in diameter, magnetite fines, cement, and water. Each ingredient of every batch was carefully weighed to ensure uniform density. Despite the heavy mixture, conventional concrete equipment was used throughout and no problems were encountered. Quality control was maintained primarily by the use of a slump test and a density measurement. To avoid segregation, the maximum allowable slump was 3 inches, and the average slump for all batches of the biological shield was 1 3/4 inches. A weight and density measurement was constantly maintained with an allowable minimum of 275 pounds per cubic foot. An average of 282 pounds per cubic foot was obtained for all batches. For corrosion protection, a bitumastic coating was applied to the inside of the steel containment shell, and then 1-inch thermal insulating board was installed. A 2-foot thick concrete wall was poured in 3 10-foot high sections. This wall supports the 20-ton rotating crane to be installed in the dome of the building. The wall also serves as a shield in the event of a nuclear incident and provides complete protection for personnel outside the reactor. In the center of the floor is the recessed area containing heavy concrete for the base of the reactor. The 30-ton thermal shield is 15 feet tall with an inside diameter of 8 feet. It is constructed of 2 2-inch steel plates with a 1 1/2-inch lead annulus between the plates with embedded cooling coils for heat removal. These 3 holes in the base match 3 similar holes in the bottom of the thermal shield. The large hole is for neutron beam access to the medical therapy shutter tank, and the 2 small holes are for heavy water inlet and outlet piping for the core tank in the center of the thermal shield. The flat surface showing on this side of the thermal shield is a guide surface for a lead door, which will permit access for neutrons to the thermal column facility. The thermal shield is designed to be a gas-tight enclosure surrounding the core tank. The next step was the installation of a 20-ton rotating crane on a circular track at the top of the 30-foot high, 2-foot thick concrete wall. This crane facilitated the installation of heavy reactor parts during construction. When the reactor is in operation, it will be used to remove or replace reactor components and aid in handling heavy accessory equipment. It is designed so that its lifting hook will always be on the building diameter. In addition to the 20-ton hook, there is an auxiliary hook of 3-ton capacity. Heat from the thermal shield will be conducted through these cooling pipes to a heat exchanger located in the basement equipment room. All critical pipes with welded joints were subjected to X-ray inspection. With the completion of the cooling coils, the 6-foot square thermal column housing was installed. This permits access to a large area for thermal neutron experiments. Next, the horizontal experimental port facilities were installed and the reactor faceplates erected. Now the reactor is beginning to take shape. The complexity of the engineering and design is readily apparent as the available workspace grows increasingly limited. With the installation of the rotating crane complete, the erection of the steel shell proceeded. The next to last phase was the placing of the hip course. Later, the inside of these plates were coated with a 2-inch application of asbestos sprayed on for thermal and acoustical insulation. The lower annular ring of the reactor was lifted into the steel shell at the same time the roof segments were being placed. This ring forms a seal with the top of the thermal shield and is the structural support for the core tank. Incorporated in the design of this piece are 6 vertical ports which abut the reactor core. The roof was field assembled using pie-shaped segments and supporting them in place with guy wires from a central tower. This is a plan view of the reactor looking directly down from the overhead crane, showing the geometry of the horizontal port system prior to pouring the biological shield. This port system includes one 12-inch port, 4 6-inch ports, 6 4-inch ports, 2 8-inch rotary ports, 1 6-inch through port, and 8 4-inch instrument ports. All ports consist of a stainless steel sleeve, a mild steel outer box, an aluminum liner to the core tank, and a shield plug. The next step after the completion of the port system was the pouring of the reactor biological shield. This shield is 5 feet thick and surrounds the reactor on all sides. It was poured in 6-inch layers at a rate of not more than 2 feet in one day. It was completely hand-placed to prevent segregation and to ensure that all difficult-to-reach areas would be completely filled. When operating at 1 megawatt, the radiation level at the reactor face will be less than 2 milliroentgens per hour. This is the inside of the thermal shield as seen from the thermal column at core level, showing the relationship of the various experimental ports. The 2 opposing pairs of horizontal tubes in the lower part of the picture are for a pneumatic rabbit system, which will irradiate chemical samples. Here again, in the bottom of the thermal shield, is the beam access to the medical therapy facility and the inlet and outlet holes for heavy water pipes. A gas seal is obtained at the thermal column by the use of an aluminum plate. This is the inside of the thermal shield as seen through the neutron beam port from below in the medical therapy room. The aluminum core tank will occupy this space. Graphite blocks were individually measured and cut according to templates. These blocks, which act as a reflector and moderator, were then placed to provide a locking pattern within the thermal shield and around the aluminum thimbles. Lead was poured between the graphite and thermal shield to aid in the conduction of heat to the cooling coils. The lower annular ring is now ready to be placed in its position at the top of the thermal shield. It is loaded with heavy concrete for shielding and weighs approximately 20 tons. Here, the lower annular ring is in place, and this is the center of the reactor being prepared for the installation of the core tank. The aluminum core tank is 1/4 inch thick, 4 feet inside diameter, and 8 feet deep. At the top is a plug which provides shielding, aids in the positioning of the fuel elements, and locates the position of the 7 control rods. It also forms a gas-tight seal with the core tank. The core tank also contains a heavy water coolant and moderator into which are immersed the MTR-type fuel elements. A unique feature of this reactor is the medical therapy room, which is located directly below the reactor core. This arrangement permits the subject to be placed in either a vertical or horizontal position, providing entirely new approaches to nuclear medical research techniques. With the core tank in place, the initial check of the various reactor systems with light water began. The experimental port facilities were inspected. The control mechanisms were mechanically tested by checking their travel. The instrumentation and operating circuits in the control room received a final inspection, and the reactor was ready for the startup. The engineering and construction of an atomic reactor such as this requires a combination of many skills. The experience gained from this project by ACF Industries is now being applied to their other reactor projects in Holland, Sweden, Italy, and the United States. With the completion of the MIT research reactor, a new and powerful instrument becomes available to further man's knowledge in the peacetime uses of atomic energy.